All right, so we are beginning our sixth unit, and you're going to see some overlap with the electron unit that we just finished. This is periodicity and bonding. What we want to do, and we're going to be continuing to do video notes, and there might be times where there's demos that you just need to be aware of, and when there are demos, then we'll be doing those in class whenever we see you. And we'll just ask you to flip to that part in your guided notes so you guys can actually see that section. So if you will, make sure and get your guided notes out. And we're going to start taking a little bit of notes today, reviewing metals, nonmetals, metalloids. Those are things you learned in physical science. We're going to talk a little bit about the groups. And then we're going to get into what's called periodic trends. And we're going to be looking at atomic radius today as a periodic trend that we want to investigate. So to begin, and I'm going to have to tell you that not everything came through with the printout. Whenever we sent it to print this time, you're going to see that not all the graphics for some reason got printed in your guys' guided notes. So I'll try and tell you what you should and don't need to write. But just some quick introductions. So whenever we look at the elements on the periodic table, they're going to be arranged in order of increasing atomic number. One general classification we can give to the elements are metals, nonmetals, and metalloids. And remember, the electron count is a driving force in behavior of how any element responds. Minus nuclear chemistry, properties, chemical properties in particular, how they react, how reactive they are when they do choose to react. All of those things are determined by the electrons. Oh, sorry. I can feel a cough coming on. Hold on. So the periodic table is also organized into what's called groups and periods. So groups are things that are going to go up and down on the periodic table, and then the periods go left and right. And we might talk equally about both, but as far as characteristics, when you think about noble gases or halogens or alkali metals, that's groups that we're talking about. And those are the vertical columns that we see on the periodic table. So if we just focus on these metals, nonmetals, and metalloids, some reminders about metals. And again, these are things that I know that you were taught in physical science because I teach that class, but they tend to be solids at room temperature. All of them are except for mercury. They have very high melting points compared to the other elements. They're good conductors of heat and electricity. And just a few characteristics. They're malleable, which means that they can be bent easily. They can be rolled or hammered into sheets. And then they're also ductile. There's a picture right there of copper wiring being made. So ductile means they can be drawn into wires. You know, copper doesn't come out of the ground like that. It's almost every metal in our ground is an ore. So what does that mean? It's most of the time it's something oxide, copper oxide, iron oxide. You know, it's in our aluminum oxide. All that stuff is in the ground as an ore. And then we have to harvest the metal out of it. We have to get rid of the oxygen that's in there. If you want to learn more about metals, you should take material science. We spent an entire unit just talking about metals, a lot more than just these details. But these are just some of the main examples and characteristics of metals. So just, you know, some ones that we put up there. Really, if you look at the periodic table, remember metalloids are going to be that bold line on the periodic table, that stair step. Everything to the left of the stair step are metals except for hydrogen. So they're different. Iron has very different properties compared to sodium. Sodium's extremely soft. It's not table salt. Sodium chloride is table salt. Sodium, the metal, is metallic. It looks like a knife when you cut it. You can cut it with a butter knife, by the way. Calcium, very, very soft metal. And we know what gold looks like, which is also a very soft metal. And so there's all kinds of different characteristics of these. They're not, copper has a copper color. It's one of the only ones that is not going to have that silver type of color to it. Oh, you get to see it twice. Okay, so nonmetals, what are some characteristics? They're, metals, solids at room temperature except for mercury. Nonmetals, they can be anything, solid, liquid, or gas. They tend to be poor conductors of heat and electricity. they tend to be dull. They tend to be brittle. Okay, where are they found on the periodic table? To the right of the stair step. So anything that's on the stair step is a metalloid. Everything to the right is a nonmetal. And don't forget the F block that you just learned about, those are all metals. Those really are to the left of the stair step when you sneak them in. So those are all metals. Those are called your rare earth metals. You can really only harvest them. There's only 2 plants in the world that is even willing, 2 mines in the world that's willing to get those out of the ground. And one is in China, imagine that. And then the other one is in California. And that's been shut down for many years because it is so dangerous to pull those rare earths out of the ground. So just kind of some interesting stuff that's going on with that. But if you look in your phone, your iPhones and even your fancy Androids, those would not work without rare earth metals. So kind of, we look at this and we think, oh, this stuff is so foreign to us. This stuff is not something that affects our lives. The beautiful colors that you get to see on your screen on your phone would not exist without rare earth metals. So, just there definitely is a piece of this. We just don't always make that connection of how they're used in our lives. Okay, so metalloids, those are going to be on the stair step. And these are just some extra pictures. Look how they look kind of metallic. Silicon has a metallic look to it. Silicon dioxide is sand, but pure silicon has a very metallic look to it. It's used extensively in circuitry because it can take a dramatic change in electrical energy and not fry the motherboard of the computers. So silicon is very, and it's a semiconductor. So that's what that means. It doesn't conduct things very well, but it conducts things enough. And computers don't want the conductivity to be extreme, or you end up frying your computer. Okay, so they want these semiconductors there. So metalloids. Okay, we would say that they have intermediate properties of both metals and nonmetals. Many metalloids are used as superconductors, that should have said, and all semiconductors, and are important in technology. So technical, and why why is California called Silicon Valley? Well, there's a lot of sand there. And that has been used to actually manufacture and use the silicon that's used in the circuitry that we see in things like computers. But just so that you know, Texas was one of the first states that actually figured out how to work with silicon chips and computers. The first place was in Texas, maybe 30 miles from where I grew up. Just saying. Okay, so on the next page, on page 2 of your notes, it says demo there at the top. We're going to do that with you guys in person, just showing you some different metals, nonmetals, metalloids, things like that for you to touch and hold. So here's the first graphic that got missed. When you look on page 2, letter D, this figure did not come through. I mean, if you want to try and chicken scratch an idea of it, then you can, but we're just wanting to point out the different groups or the main groups that we talk about. And rare earths kind of got missed on this. The F block is not even in this picture, but they're important too. So alkali metals, that's lithium, sodium, potassium, rubidium, cesium, francium. And those tend to be highly reactive metals. Reactivity is going to increase as we go down the periodic table. They have a lower boiling point and melting points. They tend to have low densities. So some of them can even potentially, I don't know if any of them can float on water. They do for other reasons. But I don't know if we have a density less than 1 for any of them. But very, very low densities compared to, things like iron that has a density that's almost 8 grams per milliliter. Alkaline earth metals, these are your berylliums, magnesiums, calciums, strontiums. Whenever, these are things that you'll hear a lot in farming as well, whether your soil is alkaline or not, depends on these metals and how many, and it's really the salts of these metals and what we find in the earth. So that's why you see that alkaline earth. Okay, we harvest all this from the earth, but they play a pretty good role in the nutrient content of soil that farmers are paying attention to. So these are also very reactive. They have higher boiling points and melting points. They combine to form common minerals, like I just said, in our earth that farmers want to pay attention to whenever they are wanting to look at the nutrient level of their soil. Then we have our transition metals, which are the vast majority of your metals. Your rare earths are fit in with your transition metals. They're a special type. They tend to be hard and dense. There are many of our common metals. You have your so the gray area, guys, that's not a group. Why is that? That's where your metalloids are. And if you go down the column, some of them are non-metals, some are metalloids, some are metals. So there's not continual characteristics as you go down those columns. So that's why you don't see names for 3 through 6. Then our halogens, well, those are fluorines, chlorines, bromines. So halides, would be salts. These are the many of your halogens like to make compounds with your alkalines and your alkalis as well. And they make salts, sodium chloride, lithium chloride, the stuff that you throw out on the ground. Calcium chloride would be a very common road salt. Halogen lights, so you hear about halogen light bulbs. So they're using these different halogens to make those light bulbs. And then the far one, noble gases. So these, we've already talked a little bit with electron configuration. Everybody wants to have this valence electron if they could. And we're going to learn more about that in this unit. But they tend to be very stable. They're non-reactive. We use argon, for example, as an insulator. So whenever you hear about double pane and triple pane windows, they still want to insulate in between those windows. It's not, and they insulate purposefully with a certain type of gas. They don't just fill it with air. Think back to the oxygen lab we just did. Nitrogen, less dense than oxygen. So what's going to make a better insulator? Something that is more dense, but is not reactive. So it probably would be a good idea to insulate with oxygen, right? Because, I don't know, Granny decides to light up a ciggy, and next thing you know, I don't know, her window pane has literally blown a hole through it. We don't want to do chlorine gas. It's green. It's going to kill you. So that's probably not a good idea. Fluorine is so reactive that there's only a couple of labs in the world that even will house fluorine gas. So not so good. So we got to go to our halogens. Well, we don't want to do helium, although that would be fun if all of a sudden you had like a helium leak in your house. Neon, not too exciting. What's the next? What is this? Why is neon not as good as argon? Because it's inert, but argon's heavier. Argon's going to be a better insulator. Okay, once you get to krypton and xenon, you start to get a little nervous about how much radioactivity is coming out of there. There's a lot of radioactive isotopes. But with argon, we've got something that is stable, and we have something that is going to be heavier than normal air, be a better insulator. So they purposely pump argon in between those double and triple pane windows to help us out. They're monoatomic. So as opposed to diatomic, like hexanohalogens, right, that we learned a long time ago, or Brinkelhoff, however you remember that, these are monoatomic. So they're plenty happy being by themselves. Okay, so, this is a real quick introduction to the periodic table. We're going to be looking at specific periodic trends as we go across look at and discover more about the periodic table. And almost all periodic trends can be explained when we go back and look at the electron configuration of an element. So we'll be using things you used from the last unit and learn from the last unit and apply that knowledge to this unit here. Here's the list of the different trends that you're going to learn. So today we're going to talk about atomic radius. There is also valence electron trend, ion and ionizations, electronegativity and reactivity. But today we're just going to focus on atomic radius, which brings us to another graphic that was missed. So normally we have a small little periodic table. So on page 3, you see a little periodic table, and then there's little graphics off to the side. I think you're just going to have to write this down. So first of all, just atomic radius, what's the definition? You choose, like maybe you just put a dash mark next to atomic radius, and you fill this in. So it's literally the distance from the center of the nucleus to the boundary of the surrounding electron clouds. So that would be the radius, right? If you think of things you've learned back in geometry class, you're looking at the radius, not the diameter. Isn't radius half of the diameter, I believe, right? So the distance from the center of the nucleus to the edge of the farthest out electron cloud. Remember, electron clouds are orbitals, S's, P's, D's, and F's. So the farthest out orbital that still has an electron housed in it, what is that distance? That's atomic radius. Okay, I'm about to show you a scary graphic. if we look, and this was not, do not even try to draw this. This was not on this sheet of paper, but let's process what's going on here. So on the left-hand side, we see atomic radius. It's measured in picometers, so super, super small measurement. Going here is just the atomic number of the element. So like, it'd be nice if I could hover over and you could actually see the number, but this would be like atomic number 1, atomic number 2. Atomic number 3, so now we're at lithium. So this is lithium, beryllium, and I'm going across boron, carbon, nitrogen, oxygen, I get stuck, fluorine, neon. This is going to number 11, okay, so sodium. So like if we go back to here, so atomic radius is biggest. If we're looking down a column, the atomic radius is biggest for lithium, and then it gets a little smaller for sodium, potassium, so on and so forth. So as I go down a column, the atomic radius gets smaller. Okay, so these are trends that we're discovering. As we go left to right, so like, again, this would be lithium. This is the next one. Oh, sorry, I just screwed up on that. This is as I went from left to right. So as I go left to right on the periodic table, the atomic radius gets smaller. Okay, wish I could write on the screen too, and you could see. So again, here's lithium, beryllium, boron, carbon, so on and so forth. So as I go left to right on the periodic table, atomic radius gets smaller. This could compare going down the periodic table. So now I'm looking at, and I'm just going to start here because it's right next to each other. This is lithium. This would be sodium. This would be potassium, okay, rubidium, and then cesium. So these top purple peaks, that would be going down a periodic table. As you go down the column, so as I go down alkali metals, what happens to the atomic radius? It gets bigger. Okay, so let's put that into the what happens. So as you move across the periodic table, left to right, what happens? The atomic radius gets smaller. So that's the trend. And you're going to have to handwrite this in because it didn't come out as a graphic. So as you move across the periodic table, left to right, atomic radius gets smaller. Here's the why. Okay, so, and we can talk more about this in person if you have questions, but more protons are added without adding extra energy levels. So, think about this. So as I'm going left to right, atomic radius gets smaller. Lithium, 2s2. So that whole thing is 2s2 and then 2p6. If we look at that second row on the periodic table, so lithium all the way to neon, we would say 2s2, and then we'd say 2p6. That's all the second energy level. I'm not adding a 3s. I'm not going 3s2, 3p6. It's all in the second energy level. So 2s2, 2p6. So I'm not adding another energy level, but I'm packing in more protons. It's like I'm making my magnet stronger. And it's being able to pull those electrons even closer to the nucleus. It's sucking them in and pulling them in closer to the nucleus, okay? So that's why as we go left to right, the atomic radius gets smaller because we're adding more protons without increasing our energy levels. We just kept it at 2s2. And that's even true when you get into the Ds because 4s, 4s2, 3d, who cares? That's smaller inside. 4p. So we didn't go from 4 to 5 to 6 to 7, 4 to, we stuck back down to 3, then we went back to 4 again. So as we move left to right, we still have our atomic radius getting smaller. Okay, what happens as we go down? As you go down, the atomic radius increases, gets bigger. Why? Think energy levels. As you go down, what are you doing? You're going like lithium, or let's start with hydrogen. Hydrogen was 1s, then you go to lithium. Well, that's 2s. Then you go to sodium. That's 3s. Potassium, 4s. You're adding energy levels as you go down. It's getting bigger and bigger and bigger. It's like I've said to some of the kids, it's like a balloon within a balloon within a balloon. So because we're adding more energy levels as we go down the periods, as we go down the columns, went from 1s, then it went from 1s to 2s to 3s to 4s. So we're adding more energy levels. So then here's another graph. If you guys just like draw a diagram of the periodic table, you don't, just that's all I really did here too. So just kind of draw what the periodic table outline looks like. And here's and I'm going to show you how we're going to get to use all of these together once we learn all the trends. But here's a basic idea. And I like to, even though we wrote it a little bit of a different way just now, I like to do it like this, where, and you'll see why a little bit later. So, likewise, as I move from right to left, it would increase. And then as I go down, it increases. And I'll show you why I write it like this once we have all those trends. So that's just us wrapping our brains around atomic radius. I do believe that here's just another graphic. That shows that as well, if you were to see the pictures. So as I move to the left, it increased if we were to follow the trend arrow you just did. And as you went down, the atomic radius increased as well. I'm pretty sure there's homework. So double check the homework that goes with this. I think you're supposed to start in that packet 1. I just don't remember. Hold on. I think we can look at the homework page together really quick. Except it really helps if I open up the correct homework slide. Here we go. This will be a good reminder. You guys, Marcus and I, we try to map out the whole unit ahead of time so that you guys have a pretty good idea of what's going on. Oh, there's just a video you have to watch. Oh, you don't even have to do anything in a packet yet? Well, that's not nice. That's wonderful. Lucky you. You only have to watch a video clip. How about that? Okay. All right. So we'll see you the next day. Some of you, maybe all of you, not sure. And we'll continue to work on this. All right. Take care.